Then this is the tension nerve preparation. We dissected the carpoprodite to suck the motor neuron and stimulate it, and also we dissected the segment that we want to get the tension nerve. Then we remove the closer muscle fibers, and the tension nerve is located close to the opener muscle fibers. Then we sucked the tension nerve into the recording electrode, and we stimulated the motor nerve, and now we get the electrical activity from the tension nerve. Then we stimulate a different stimulation paradigm, like 20 hertz at flex position. Then you see the stimulation artifact, and also we see small spikes here, like this one, but the spikes they are not too big. Also another small spike here. Then you can record it for a certain period of time for each stimulation paradigm. Like I mentioned, this one is 20 hertz. Then we stimulate at 40 hertz at the same flex position. You see our stimulation artifact. And also you see small spikes and this big spike. Then we can look at this big spike by zooming in. It's a very nice spike. Then we can see more spikes here, like this one, this one. Then we see small and also big spikes. This is at 40 hertz. Then we stimulate at 60 hertz to see what's the difference between different stimulation paradigms. Then you see that spikes, a lot of spikes here. Also you can see like small and big spikes, and also this one is bigger than this one. Then we can zoom in this one, look at it. And sometimes this is stimulation artifact. Then you can see two spikes here. Then we stimulate at 80 hertz. Then this is stimulation artifact, and we see some small spikes and a big spike. And also you can see two spikes here. Then we can zoom in this one, and you can see this is stimulation artifact and this one, and you see two spikes here. And also this one, we can compare this one with that one. You see that this one is bigger. This one is bigger than this one. Then here, when you got all these recordings at different stimulation paradigms, then you can take a certain like specific time, like 1 second or 2 seconds for each stimulation paradigm, like 2 seconds in 20 hertz, 40 hertz, 60 hertz, and 80 hertz. Then you can compare the number of spikes in each stimulation. Then we have a lot of spikes here. Then this is at a fully flexed position. We stimulate at 60 hertz to see what's the difference between when it's at like a fully flexed position at 60 hertz and at half flexed at the same stimulation paradigm 60 hertz, then at a fully extended 60 hertz. We just change the position of the dactylus here, but we don't change the stimulation. It's 60 hertz. Now I'm going to show you the fully flexed position of dactylus at 60 hertz. Then you can see the spikes here. And like I mentioned, this one is stimulation artifact and this is the spike. You see all the spikes. When it's in a fully flexed position, then more force will generate it. Now we stimulate at 60 hertz in half flexed position. Then you see stimulation artifacts and some spikes here, but at half flex position less force will be generated, but we still see spikes here. Then now it's in a fully extended position and we stimulate at 60 hertz, and you see we don't see too much like too many spikes here. You can see one spike and another here. Then the frequency of spikes decreased here. You see one spike there, another one, and some small spikes here. We see less spikes because at this position less force will be generated. Then this is in a fully flexed position. We stimulate at 60 hertz, and you see the spikes here and some small spikes too. We wanted to know then what happens when we release it very quickly, which is called like quick release. But still it's in flex position and we stimulated at 60 hertz. Then when we release it very quickly, you see that you don't see any spikes here. When it extends out, then the tertiary nerve activity stopped here. Then it will come back again when it's extending out. We see one spike, then another, then we see spikes here. Then it means that during flex position we saw a lot of spikes, but when we release it very quickly, then the activity stops for a while, a short period of time, then it comes back again, but it won't be like it's fully flexed. Then also we measure the force of the crab walking leg at the flexion position. Then we can measure the force at different positions, like at the 90-degree and also at fully extended position. But here, this recording, we got it at flex position of the walking leg. And but we have to convert these forces into numbers, and now I'm going to show you how to get the rate of rise at a certain amount of time, like for 1 second, then how much force is generated. Then here we have different stimulation paradigms. We stimulated at 20 Hertz, 40 Hertz, 60 Hertz, 80 Hertz, and 100 Hertz. Then we can zoom in one of these traces. This is at 20 Hertz. Then we should look at the beginning of the rising phase here and put a marker. You see marker here, and put the marker at the beginning of rising phase. Then if you look at this, you see that it shows the time. Then now it's 1 second. Yeah, here if you look at this one, it's 1 second. Then after rising 1 second, then how much force is generated, then we can get it here. It's about 0.7 microvolt. Because it's electrical, then it measures at a microvolt. Then we can write down this measurement. Then after 2 seconds, then we can measure it after 2 seconds. Then we see that's 2 microvolt. Then after 4 seconds and 5, 6, and 7 seconds, then we can get all this data and make a graph. Then also we can do the same thing for 40 Hertz and put the marker at the beginning and get all this the rate of rise at 1 second, 2 seconds, 3 seconds, 4 seconds, and at 60 Hertz, and also at 80 and at 100 Hertz. Then we can collect all this data and make a nice graph, and to show what's the difference of the rate of rise at different stimulation paradigms. Because you know that when you make a graph, then you know that when you increase the stimulation, then the motor neurons fires a lot, and it contracts the muscle fibers a lot, and it makes more force. Then you see that the rate of rise increases. Then now I'm going to calibrate the force transducer. You see the force transducer that you use it to get the force generated by the crab walking legs. That the force transducer is connected with the bridge pod. This one is a bridge pod. And also the bridge pod is connected with the power lab ID here. There's an input. I plugged it into number 1 input. Then I also make sure that it's on. Now I'm going to open lab chart 7 here. Then now click on setup channel settings. We just need 1 channel. And also we can click on channel 1 and go to bridge pod here and make sure that the time stand gain is checked. Then okay, then we can also we want to collect at like 10K here, and also go to the higher gain like 500 microvolt, then hit start. You see that's very fast. Then and also you see that it's not on 0. Then we can use this knob to, you see that's very sensitive. And also to make it slower, we can hit on this, compress the horizontal line. You see that makes it slower. Now I'm going to use different weights here, like 1 gram, 2 gram, and you see that every weight is attached to a string, and you can make a string. And also it's better to grab those ways with a tweezer, because if you like touch it, it might corrode the it's a brass, it corrodes the brass. And also now we can hang it with this. Also you see that it's a little bit up, then we can stop it here and put the marker M here and also the cursor over here, and you see it's about 16.4 microvolt. Then if you move the cursor, you see that you get different numbers, but the best way to do this is to get the average. Like you have 17.6, 15 and 14, then 16, and we can take 16.3 microvolt. Also we can do smoothing here, then hit the channel and also go to smoothing. Then if you go higher here, like 50 or 100, let's try 50 first. I see that it makes it smoother. And also we can go higher, smoothing like 100. It makes it smoother. Then put the marker here again and go up, and it's about 16.4 microvolt. Then we should take that note, like you say that 1 gram is equal to 16, and it said 16.4 microvolt. Then let's try another way. Then just remove that one, put it again, and we have 2 grams now. And before that we have to hit start. And also stop it again, and get back the marker and put the marker here. If you go here, you can see that it's about, then you see that it makes those big bumps, because when we want to hang the weight on it, then we put a little bit pressure on it, more pressure, and you see those bumps. And also if the wind blows through it and also it makes bumps, then it's better to let it run for a while, then we can then stop it. Then you see that the M marker is there, and you can put the cursor over here, and it's about like 29.1 if you want to take average microvolt. Then 2 grams, you say that equal to 29.4 microvolt. Then let's try this time 5 grams. We tried 1 and 2. Then let's try 5 grams. And make sure that it's on 0. Like I said, you can use this to zero it. And now it's on 0. Let's put the 5 gram weight on it to see. Like I said, you see those like bumpers. Then let's run for a while. And now we can stop it, and also click on here to get the marker back, and put the marker here. Then you can see that it's about, we can take average 75, 76, 78, like 76 or 77.2. Then we want to check it on balance, because it might be a little bit off, because we put the string on it, and it might not be just exactly like 1 gram, because we have to like weight with the string. And also there's some of them, there's a rust on it, then therefore it's better to double check it again. Then I'm going to use the sensitive balance. You see that it's covered because it's very sensitive. When the wind blows through it, it changes the numbers. Then I will weigh those to make sure. At the beginning we have to hit the like on button. Then also we should tear it, like it should be 0, all the numbers here. Then now it's ready. Then we open this, and this one, it should be 1 gram, but you know that the strings will be more than 1 a little bit. And close this, and we see that it's not exactly 1 gram, it's about 1.0029. Then now we got all this accurate weights, then we can convert the electrical signals that we got from the stimulation of the walking legs or crab, and we can convert those forces or tensions into grams. Then if you wanted to take gravitational force into consideration, then we have to convert those weights into newtons. But you can use that one in grams, that would be okay too. After when we got all this data of the force that's generated by the stimulation of the crab walking leg, and we recorded on the computer using a lab chart, then we have relative force generated. It's in microvolt, and the time in second. Then we looked at the force generated in microvolts in 1 second at different stimulations: 20 Hertz, 40 Hertz, 60 Hertz, 80 Hertz, and 100 Hertz. Then we looked at it for 7 seconds. And also, if you look at, you can see that if you compare the lower frequency with the higher frequency, then we can see that the higher frequency, more force is generated. And like I mentioned before, that because the motor neurons fire many action potentials, and then it causes the contraction of a lot of muscle fibers, and it generates too much force. Then, but here it's better to look at the initial rate of rise because it's linear. Then we made another graph to show that one too. This is 1 second and 2 seconds. This is the initial rate of rise at different stimulation frequencies. Then you see if you can compare the slope of 20 Hertz with 40 Hertz, then 40 Hertz with 60 Hertz, and also 80 and 100 Hertz. If you look at the 20 Hertz, if you compare 20 Hertz with 80 Hertz, that you see that the slope is increased here at 80 Hertz. Then it means that it generates more force. And also, if you compare the 80 Hertz with 100 Hertz, it shows that it's plateaued off because it might generate the maximal force at 80 Hertz. Then you can make a graph like this and also compare the slopes at different stimulation frequencies. But here we have a relative force generated in microvolt. We should convert this into weight. We already calibrated different weights. Then we made this graph. This is in weight. We had 2 grams, 1 gram, 2 gram, and 5 grams. And we made this graph. And also we have microvolts in y-axis and weights on x-axis in grams. And if the force is 20 microvolts, then you can approximately look at it. You see that this is about 1.25 weight in grams. Then we can convert all the microvolts that we got into grams. But here, because of the gravitational force, then if you want to be more accurate, then we can convert the weights into newtons. How can we do this? Then we can get force in Newton by using the weight that we got before. And also we can use this equation, then this force by weight equal to mass in kilograms. Then we have this mass, then times acceleration, squared acceleration in meter per square second. Then this acceleration is gravitational pull, and we have to get the gravitational pull like according to the latitude of this region. And also then we can get in Newton, which is in kilogram times meter per square second. Then, like I said, we have to standardize the weights, and you can go online and get the conversion factor according to the region that you are doing your experiment. But we can use this 9.8.
I hope you enjoy listening in on the tension nerve and producing photos to learn about these sensory structures. These are challenging electrophysiology preparations, so you have to be patient. My suggestion is to meditate or listen to peaceful music before coming to class.
As I mentioned before, that the tension nerve firing frequency are affected by neuromodulators. Then you can apply serotonin or 5-HT to see how it affects on the tension nerve firing frequency, and then compare it with the normal tension firing frequency, since it's known that 5-HT increases the amplitude of postsynaptic potential or EPSPs, and also it increases the miniature postsynaptic potential or minis, through increasing the release of glutamate into the synaptic cleft. Then try to think how 5-HT increases the firing rate of tension receptors. You might ask the question whether serotonin directly affects the tension receptor or indirectly. I will leave this to you to figure it out.